In this problem, we're going to practice going through a Carnot cycle analysis on the following system, in which we have an ideal gas with this molar heat capacity that's going to undergo a Carnot cycle where the temperature of the hot reservoir is 500 degrees Celsius and the temperature of the cold reservoir is 300 degrees Celsius. We're also provided a table in which we're told the volumes at the beginning of each step of the Carnot cycle. So during the isothermal expansion, the volume at the beginning of that step is 1 meter cubed, and at the adiabatic expansion, the volume of that step is 1.7, and so on and so forth. Okay? And so for this step, what we want to do is we want to calculate the amounts of heat and work during each of the steps. And then we also want to calculate the overall efficiency of this cycle. Okay? And once again, temperature of the hot reservoir is 500 degrees Celsius. Temperature of the cold reservoir is 300 degrees Celsius. And so with this information, what I want you to do is pause the video here and sketch out the system for yourself. With this information, we could sketch a Carnot cycle system that looks like this, where we have some sort of hot reservoir at a temperature of 500 degrees Celsius that donates heat to the system, which is going to be our gas. And then we also have a cold reservoir, which is going to take some heat, QC, from our system. And the temperature of this cold reservoir is 300 degrees Celsius. All of the volumes of our system at each of the steps is listed here. And we also have our heat capacity information. We were told the constant volume heat capacity, but we know that for an ideal gas, we could easily get the constant pressure heat capacity just by adding on the gas constant, so that we get about 30 joules per mole K. The other thing we want to calculate at the end is the overall efficiency of our Carnot cycle, right? And when you're thinking about efficiency, just kind of always remember this definition, that it's going to be what you want. So in our case, for this cycle, we want work, or we want power. And then what we want to pay is we have to donate some heat to the cycle, some energy. Okay? And so in terms of things we're going to calculate, essentially this is going to be the overall work we get out of the system divided by the heat we have to give. And this negative here just accounts for the fact that all the works, during the net work that we want is going to be leaving the system. Okay? All right, and so this is just as a reminder, this is a generic definition of what efficiency is. Okay? All right, and so here's the description of our Carnot cycle. But just as a reminder, here I just want to sketch out what the different steps of the Carnot cycle are. Okay? And so for the first step of the Carnot cycle, we're going to have some sort of isothermal expansion. In which our system goes from some initial volume, V1, to some volume, V2. And to do that, there's going to be, since we're expanding, the system is going to be working on the surroundings, or in other words, there's going to be some W1 that's exerted. Okay? Step 2 is now going to be an adiabatic expansion, where we go from the same V2 that step 1 ended at, now to some V3. And since it's still an expansion, work is still exerted. Step 3 is going to be now an isothermal compression, where we go from the V3 we left off at now to some V4 that's smaller, right? And to do that, the surroundings have to supply work to the system, to our gas. And so here, the system is going to be receiving work. And then finally, adiabatic compression. Where we go from V4 back to our original V1, and since it's still a compression, the system is still going to receive work. Okay? So let me move these closer to save some room at the bottom. Okay. All right. And so here's just writing out in words what's going on. But we could also sort of sketch what's going on as well. So to do that, I'll sketch it like this, where in our different states, so initially we start off at some temperature hot, some pressure 1, some volume 1. And then we undergo that isothermal expansion. And since it's isothermal, the temperature is going to stay constant, but pressure and volume are going to change, right? And so we would call this step 1. And during this step 1, the system is going to receive some heat, and it's going to give out some work. Okay? All right, and so for step 2, it's adiabatic. So here, we're going to change temperature, pressure, and volume all at the same time. So this is now step 2. And here, the system gives out some work. Step 3 is once again isothermal step, so the temperature is going to stay the same, but pressure and volume are going to change. And the system is also going to donate some heat to the cold reservoir. And then finally, in step 4, we end up back at the initial conditions. This arrow should be going the other way. Okay? All right, so visually, that's sort of what's going on with this Carnot cycle. Now, when dealing with these Carnot cycle problems, or really any of these cycle problems, we're going to be dealing with a lot of information. And so to organize ourselves, it's always nice to set up a table in which we have our properties that are changing. So in this problem, we know that volume and temperature are going to be different at each of the steps. And what we want to calculate are the various works, heats, and also changes in entropy that occur at each of these different steps. Okay? And so as we go through each of the different steps of the cycle, we're going to collect all our information there. All right? Now for every step of this cycle, we're going to apply the same assumptions. So the assumptions that we'll make is we're going to be dealing, since it's a Carnot cycle, we're going to be dealing with a closed system. We're not going to care about changes in kinetic or potential energy. In this problem, we're dealing with an ideal gas. And also, since it's a Carnot cycle, all the steps are going to be reversible. And so that means that in our entropy balance, the entropy generated is going to be equal to 0. Right? in all of the steps, we're dealing with a closed system, and so that means our material balance is going to be fairly simple. We have no reaction. It's closed. Therefore, final is going to be equal to the initial steps, or the amount of moles. Alright? And so what we could say is that the moles we start with are equal to the moles we end with, and we'll just call those N. And in our problem, we're assuming a basis of 1 mole. Okay? Alright, so we could apply all of those assumptions to each step of the Carnot cycle. Okay? Alright, so now we could go through our analysis. And so what we'll do is we'll just proceed. Let me clean this up. We'll just proceed through the different steps in order. Okay, so we're going to start with step number 1. So step number 1 is the isothermal expansion at a temperature of TH. So that's the temperature of the hot reservoir. Alright, we're dealing with a closed system, and really we just care about the initial and final states of the first step. So that means we're going to use the difference form of our closed system energy balance. We don't care about changes in kinetic or potential energy. And it's isothermal, and so for an ideal gas, du is going to be equal to 0. And so what we find is that if we integrate this out, we get that the heat for our system, so in step 1, which we know is going to be equal to the heat that has to go into the system from the hot reservoir, and that's just equal to the negative of the work that the system has to give to the surroundings in order to expand. Alright? So, if we could figure out work, that means we could figure out what the needed QH is. To get work, since we're dealing with a piston cylinder system, we just need to go to our mechanical work definition. And then by doing a force balance on the piston, we could show that the force of the system is just equal to the pressure of the gas times the area of the piston dx. Right? The area of the piston, even though we don't know it, we know that it's a constant. Okay? So we could combine it with dx, and then we could transform that into a volume, just like we've done before. Alright? Now, the next step here is we got to figure out what P gas is. We have to remember that in the Carnot cycle, each of our steps is reversible. Right? And so since we're following a reversible quasi-static sort of process, that means for the gas, we could approximate what it is just using equation of state. In our case, we could use the ideal gas law. So we'll plug in the ideal gas law for P gas. So nRT, and then the volume is over here. And we know this TH is a constant, or T is a constant, it's equal to TH. And we also know that the moles are constant as well. So when we integrate, all we have to integrate is the V here. And what we get is that W1 is equal to nRTH natural log of V2 over V1. We know everything on the right hand side, so all we need to do is just plug in. And what we get is that the work is equal to 3.41 e to the 3 joules, or negative 3.41 kilojoules. So we figured out what the work is, and then from our energy balance, we know that QH is just equal to the negative of work. So QH is just going to be 3.41 e to the 3 joules. Alright? Now the last thing, even though we don't need it explicitly for the problem, it's always good to just check. Is we could take a look at our entropy balance. So ds is equal to dq plus dsgen. Alright? Now for the system, it's isothermal. Well, first of all, it's reversible, so we don't need to worry about this. This is 0. And then we also know that it's isothermal, so T here is just going to be TH. And this is going to be DQH, right? And we know, based on our energy balance here, that dq is just going to be equal to the negative dw. And since we're negative well, let me write it out. Negative dw. And we know that since this work is just the mechanical work, our negative dw would then just be this. And once again, we know that F system is equal to P gas times the area of the piston, right? We could combine area of the piston to here to get volume, and P gas, once again, is just this stuff. So the temperatures are going to cancel out here, and what we're left with is that ds is just equal to nr dv. So if we integrate, we get that delta S is equal to nr ln of v2 over v1. It's essentially just the negative of our work result, except now we're dividing by th to get this. Okay? Alright, and so since we know all the values there, if we plug in, we get that the change in entropy is 4.4 joules per Kelvin. Okay? So now we've calculated delta S, Q, and W. We could plug all those things in for our first step at the very top in our table. So negative 3.41 e to the 3, 3.41 e to the 3, and 4.4. Okay? Alright, and so for the first step, I went in detail about how you would derive all the equations for work, heat, and entropy.